Hi, my name is Shirisha. In this project, I implemented the continuous bag of words model completely from scratch using NumPy. The main objective was to understand what happens inside a word embedding model without relying on high-level deep learning frameworks or automatic differentiation. In this project, it covers implementing SIBO, from scratch using pure NumPy, no PyTorch, no TensorFlow, no AutoGuard, implementing the complete forward pass manually, implementing the full softmax output layer, computing cross entropy loss manually, deriving and implementing analytical gradients for W context, W word, training using mini batch stochastic gradient descendant SGD, training on a corpus of approximately 100K tokens, vocabulary size of approximately 5000 words, embedding dimension K is equals to 100. SIBO architecture predicts a target word from its surrounding context words. For example, the cat is sitting on the mat. If the target word is sitting, the surroundings words are used as input context. The context word embeddings are combined and the model predicts the probability distribution of the target word using a full softmax layer. The mathematical components, the implementation includes forward pass, context embeddings, hidden representation, softmax, word probabilities, and the loss. Cross entropy loss is calculated between the practical probability distribution and the actual target word, and the backward pass. The analytical gradients for the model parameters are derived and coded manually. This provides a complete understanding of how the SIBO model learns word representation. Gradient verification. To make sure the manually derived gradients are correct, I implemented a finite different numerical gradient trick. The numerical gradient is compared with the analytical gradient. The maximum relative error is reported with the required condition. Maximum relative error is less than 1e minus 6. This verifies that the hand-derived backpropagation implementation is mathematically correct. Training experiment. The model is trained using approximately 100K tokens. Vocabulary is 5000. Embedding dimension is equals to 100. Mini batch is SVD. Full softmax output layer. The training loss curve is plotted to observe whether the model converges during the training. Effects of the context window. Three context window sizes are evaluated. D is equals to 1, D is equals to 2, D is equals to 5. A smaller window focuses more strongly on nearby syntactic relationships, while a larger window provides broader contextual information and can capture more topical or semantic relationships. The loss curves are compared to study the effect of context size on convergence. Effect of learning rate. Different learning rates are tested to understand their effect on training. A learning rate that is too small can make convergence slow. A learning rate that is too large can cause unstable training or prevent the loss from decreasing smoothly. The experiments compare convergence speed and final training loss. Nearest neighbor analysis. After training, cosine similarity is used to find the nearest neighbors of the selected query words. For example, king, computer, school, city. The results help evaluate whether the learned embeddings capture meaningful relationships between words. Softmax bottleneck. The implementation also measures the time spent computing the softmax denominator. The denominator requires considering the entire vocabulary. Therefore, its computational cost grows with the mod V. With approximately 5000 vocabulary words, this full softmax operation becomes an important computational bottleneck. This experiment demonstrates why large-scale word to implements of often use alternatives such as negative sampling or hierarchical softmax. Thank you.